In this video, we're going to look at quadratic functions. Now, quadratic functions can be written in a number of ways. And for that matter, a quadratic function is going to have very similar features to a quadratic equation in two variables. So a quadratic function or equation can be written as either function of x or y is equal to ax squared plus bx plus c. This form is called the general form in our book. Other books may call this a different thing, but we call it the general form in our book. Another way a quadratic function can be written is f of x is equal to a times the quantity x minus h squared plus k. Or y equals a times quantity x minus h squared plus k if we have a quadratic equation. Our book calls this the standard form. Other books may swap that language. Now, in both cases, the key thing here is that our variable is being squared. Our variable x here is being squared. It has coefficient of a, and then we have bx plus c in the general form. In the standard form, we have x minus h squared. When I expand this, I'll get an x squared term and likely an x term and an x term, as long as h is not 0. And then you could simplify it. By the way, this letter A is the same in both cases because if you expand x minus h squared and then multiply by a, the coefficient of the x squared will be an a. So the quadratic function or the quadratic equation in general form and in standard form have the same a value. It's easy to see that the quadratic function in standard form is just our base quadratic function shifted right h units, up k units, and then we have a vertical stretch of a. By the way, you don't need a horizontal stretch because that can always be factored out and put in with your vertical stretch. So the graphs of these quadratic functions are going to be parabolas. They're going to be transformations of parabolas. We've dealt with transformations of parabolas before. Remember, our base quadratic function is f of x is equal to x squared. That's also called the toolkit function. And then it's pretty obvious in the standard form that if a is greater than 0, then the parabola is going to point up. If a is less than 0, then the parabola is going to point down. We've horizontally shifted by h units. We've vertically shifted by k units. And then there was a vertical stretch of a as well. So if I graph an example, we have f of x is equal to 1 times x minus 3 squared plus 2. That's a right shift by 3 and an up shift of 2. And then there's no vertical stretch that was involved or vertical stretch of 1. If I make my coefficient, my a, be a 2, then we've vertically stretched this by 2, starting at the vertex. And if you put a negative in front, then everything flips upside down. So we can see what happens in this case. So each quadratic function is going to be a transformation of my base quadratic f of x is equal to x squared. That's not just in this standard form, but that's also in the general form as well. Now, other features of the parabola we get when we graph this, it's going to have either a maximum point or a minimum point called the vertex. The domain is going to be all real numbers. You can plug in any x value you want. The range is either going to go from that maximum point down to negative infinity if the parabola points down, or it's going to go from the minimum point up to positive infinity if the parabola points up. Like I said, the vertex of that parabola is the lowest or the highest point, depending on whether the parabola is pointing up or pointing down. Another feature of the parabola is that every quadratic function leads to a parabola which has a axis of symmetry. The axis of symmetry is a vertical line running through the vertex. And if you look at that vertical line, on the left-hand and right-hand side of it, it is symmetric. The parabola, that is symmetric. If I look at my parabola, the one I have, f of x is equal to -2 times quantity x minus 3 squared plus 2. The axis of symmetry would be this line of x equals 3. And you can see it's symmetric because if you move a certain distance to the right, you'll hit your parabola on one side, and move that same distance to the left, you'll hit the parabola on the other side. So this vertical line of symmetry. Notice that to get symmetry, the vertical line has to go through the vertex. In this case, since our parabola was pointing down, it was a highest point. If our parabola points up, then the vertex becomes the lowest point. Because the vertex and axis of symmetry are interesting features of the parabola, we want to be able to find them. If we're in standard form, then the vertex is fairly obvious. Since we've shifted h units left and right, and k units up or down, left or right, and then up or down, then the vertex is just h comma k. And since the axis of symmetry has to be a vertical line going through the vertex, it has to have form x equals h. Therefore, if we have the standard form of a quadratic equation or a quadratic function, that is quadratic equation in two variables, or a quadratic function, then the vertex and axis of symmetry are fairly straightforward to find. Let's do a couple of examples. Here we have a quadratic equation in two variables. Here we have a quadratic function. We know that they do that. So we're going to find the vertex and axis of symmetry of these quadratic functions / equations. And we'll also give the minimum or maximum value of the function. If you want to try this on your own, you can push pause on the video and do that. So here we go. What we're going to do is we're going to start out by finding the vertex. Vertex on this one is pretty straightforward. Again, x minus h, so that means h is 3. And then plus k, so k is a negative 7. So the vertex is at point 3 comma negative 7. Now the axis of symmetry is going to be a vertical line, so it's going to be x is equal to, and it has to go through the vertex, so it has to have x is equal to the same x value as our vertex. So in this case, x is equal to 3. Since this parabola has a positive a value, our a here is a positive 2, we know the parabola points up. Since the parabola points up, let me write that down. That means the vertex is going to be the lowest point on the parabola. That means this parabola has minimum value, so minimum y value that is, of negative 7. So the minimum y value for this parabola is negative 7. Again, I know it's the minimum because the vertex is the lowest point. I know my parabola is pointing up in the air. Let's do a similar thing with this f of x. Here we have f of x is equal to negative quantity x plus 5 squared minus 3. So the vertex I just read off is the point negative 5 comma negative 3. Be careful about that. Sometimes people will mistakenly write a positive 5, but it's x minus h. Therefore, h is a negative 5. And then it's a plus k at the end. Therefore, k is a negative 3. Axis of symmetry. Vertical line, so x is equal to, going through the vertex means x has to be equal to negative 5. This a value is negative, so the parabola points down. And therefore, my vertex is going to be the maximum point. And so the maximum value of any y value on the graph will be the y value of negative 3. So the maximum y value on the graph has to be the y value of the vertex. By the way, again, remember there is no maximum x value or minimum x value because the domain goes from negative infinity to positive infinity. The vertex is fairly easy to find in the standard form. As long as we remember the standard form has form x minus h inside the parentheses and then a plus k outside of the parentheses. Now, what about in the general form? How can we find the vertex and the axis of symmetry if we have y equals ax squared plus bx plus c? Well, it's not going to be quite as easy as just writing down some number that I see in the equation. I'm going to have to do a little bit of work. Not much work, but just a little bit of work. It turns out if y is equal to ax squared plus bx plus c, then the vertex is going to have x value of negative b over 2a. I won't go through why that is right now. We might see why that is a little bit later, but the vertex always has x value of negative b over 2a. And therefore, the axis of symmetry is also going to be x equals negative b over 2a. Now, if the vertex, I know the x value of if I know the x value of the vertex, then I can always find the y value by just plugging in the known x value. So if the x value is 2, then I know I can plug in 2 and get the corresponding y value. So let's do another example. Let's find the vertex and axis of symmetry of these two quadratic functions. And then also we'll give the minimum and maximum value of those functions. If you want to push pause on the video, go right ahead. I will do these two problems in just a second. So we have this general form, at least what our book calls this general form. Other books may call this the standard form. And if we have that, then I look at x is equal to opposite of b over 2a. In this case, that is negative 6 over 2 times 1. So we get negative 3 as the x value. Now that's going to be the x value of the vertex, and it's also going to be the equation of the vertical line, x equals negative 3. If I want to find the vertex, I need to do one more step. I need to find the y value. And that just consists of plugging in negative 3 into my function. So f of negative 3 would be equal to negative 3 squared plus 6 times negative 3 minus 10. And when you do that, you get 9 minus 18 minus 10. That's a negative 19. Now we can do everything that we did earlier. We say vertex is the point negative 3 comma negative 19. The axis of symmetry is the equation x is equal to negative 3. This parabola has a positive value in front of the x squared term. That's the a value. So since a is positive, this parabola points up. And therefore, the vertex is going to be the minimum point. So the minimum y value is negative 19. Hopefully everybody understands why parabola points up. Parabola points up because we have a implied 1 in front of the x squared. That's a positive 1. Therefore, we're pointing up. We can do the same thing with this equation in 2 variables if we'd like. We start by finding the x value for our vertex. X is going to be equal to opposite of b all over 2a. which in this case is going to be negative. In the numerator, I have a 9. In the denominator, I have 2 times negative 3, which becomes negative 9 over negative 6, which gives me a positive 1.5. Then I can find the corresponding y value by plugging in 1.5 into my function. Negative 3 times 1.5 squared plus 9 times 1.5 plus 8 becomes a 14.75. And therefore, I know a couple of things. The vertex is going to be the point 1.5 comma 14.75. The axis of symmetry is the vertical line x equals 1.5. This parabola points down. So my vertex is going to be a maximum value. And so I get a maximum y value of 14.75. You could convert that into a fraction if you'd like, 14 3/4. You could convert it into a mixed number. You can do what you like, but 14.75 is the maximum value, maximum y value. So there you go. This opposite of b over 2a trick can lead to us finding the vertex, finding the axis of symmetry, and then using that along with the fact of whether the parabola points up or down tells me whether I have a minimum or a maximum y value. And that minimum or maximum y value will be the y value of the vertex. Also, if you're ever in doubt, you can check your answer by graphing, either by using something like Desmos or utilizing your calculator like a TI-84 and graphing that way. But you can see on Desmos, Desmos will highlight the vertex if you click on it. And sure enough, I got 1.5 comma 14.75 as the vertex of that parabola. So there we go. Now we can find a couple of important features of a parabola, namely the vertex and the axis of symmetry and which direction the parabola points, pointing up or pointing down. By the way, I say that this is a parabola pointing down when it's going off to negative infinity. And if we had a parabola pointing up, it would look like this because the y values go off to positive infinity. So parabola pointing down, parabola pointing up. A couple of other important features of a quadratic function or a quadratic equation in two variables are the x and y intercepts. So the x and y intercepts of a parabola, well, we've already seen what, hopefully in a previous video, we talked about x and y intercepts of functions. The x-intercept is where the graph hits the x-axis. The y-intercept is where the graph hits the y-axis. On a parabola, or on a quadratic function, a quadratic function will have one y-intercept, always. But on a quadratic function can have either 0, 1, or 2 x-intercepts. Now, if we want to find the x-intercepts and find the y-intercept, it's just like we've done previously in other sections. If I want to find the y-intercept, I plug in x equals 0. That will lead me to a point 0, comma, a y value, which will be a y-intercept. If I want to find the x-intercept or x-intercepts, then what I do is I'd replace my output value, my y value, with 0. And that will force me to have to solve a quadratic equation. So if we're finding the y-intercept, I just plug in 0 for the x value, and then I just evaluate it. If I'm trying to find an x-intercept, I plug in the 0 for the y value, and that will give me a quadratic equation to solve. By the way, in our previous example, we can see why a parabola would either have 0, 1, or 2 x-intercepts, because the parabola on both sides of the axis of symmetry it may cross the x-axis twice, or if I had this situation, my parabola doesn't cross the x-axis at all. So that would be the 0 or the 2 example. And then it hits the if it hits the x-axis at the vertex, then that's where we get one solution, one x-intercept. But most of the time we'll either have 0 or 2 x-intercepts, and every time we have one y-intercept, because a parabola will cross the y-axis at some point. It can't cross the x-axis at 2 points because that would negate it being a function. It would fail the vertical line test. So let's take an example here and just kind of ask some broad general questions. If we wanted to find x and y intercepts of this, and let's say we want to do it algebraically without trying to utilize the calculator, what would we actually do? Well, in this case, if I wanted to find the y-intercept, let's say I want to find the y-intercept first. All I would do is plug in an x value of 0, and that's pretty straightforward. I get 0 squared minus 2 times 0 minus 5. And so I'd get a y value of negative 5. Therefore, my y-intercept would be the point 0, comma, negative 5. So that's what we mean by just plug in 0 for x. So plug in 0 for x and then evaluate. This gives me the y-intercept of 0, negative 5. The x-intercept's a little bit more difficult because when we try to plug in y value of 0, I'll leave it like that. I get 0 is equal to, so I replace my y value with 0. 0 equals x squared minus 2x minus 5. Let me clean that up a little bit so it looks right. And then I would need to solve this quadratic equation in one variable. So I have a quadratic equation in one variable that I need to solve. And that's going to require some quadratic equation solving tools. And that's what we're going to look at right now. If I want to solve a quadratic equation in one variable, there are multiple ways of doing that. The first one we're going to look at is factoring. Then we'll take a look at the square root property. I'll briefly mention completing the square, and then we'll take a look at the quadratic formula. So these are 4 different algebraic methods for solving a quadratic equation. Let's take a look at factoring to begin with. Let's say I want to solve a quadratic equation through factoring. If I want to do that, then I'm going to force the form of that quadratic equation to be ax squared plus bx plus c is equal to 0. So it looks kind of like the general form equal to 0. And then I'm going to factor the left side into 2 linear pieces where each of them is going to be multiplied times the other. And obviously the right-hand side is going to be 0. Whenever I have 2 numbers multiplied to give me 0, then one of those numbers has to be 0. So once I've factored the left-hand side, I can set each linear piece equal to 0 and then solve each equation individually. This is how we can solve quadratic equations through factoring. Let's do an example. Here we have x squared minus x minus 20 is equal to 0. Let's solve this via factoring. In this video, we're not going to take a look at a comprehensive factoring polynomials study. There's lots and lots of different ways to factor. What I'm going to focus on mainly is if our coefficient of the x squared is a 1. If our coefficient of an x squared is a 1, and we have equal to 0 on the other side, what I'm going to do to factor this is I'm going to look at factors of negative 20. And if I look at factors of negative 20, it's like 1 times 20. I'm sorry, 1 times negative 20 would give me a negative 20. All right. And also another factor would be negative 1 times positive 20. Another factor pair, I should say. And another factor pair would be 2 times negative 10. Another factor pair, maybe I should write a parentheses or a 0 around there. Let's do a comma for separation. Another factor pair would be negative 2 times a positive 10. 3 is not a factor of 20. The next factors of 20 would be negative 4 and positive 5. And then after that, a positive 4 and a negative 5. So I look at all these factor pairs of negative 20. This is all of them over the integers. The two that add to give me a negative 1, which happens to be the coefficient of this x, are the 4 and the negative 5. So that means I'm going to use that pair, the 4 and negative 5, and my equation, this x squared minus x minus 20 equals 0, can be rewritten as x plus 4 multiplied times x minus 5 is equal to 0. So quantity x plus 4 times quantity x minus 5 is equal to 0. Again, I look at factors of this term that add to this middle coefficient. That works every time the values of x, the coefficient of x is 1. Now I can set each piece equal to 0. So what I mean by that is now either x plus 4 has to be 0 or x minus 5 has to be 0. This gives me two solutions. One is x is equal to negative 4. That's what I get when I subtract 4 from both sides. The other is x is equal to a positive 5. That's when I add 5 to both sides. So that's the idea of factoring. I start with a quadratic equation which has 0 on one side. I factor the other side into two linear pieces, and then I set each one of those linear pieces equal to 0, and then I solve each one. This gives me two solutions to this quadratic equation. And if you plugged both of those in, if you plugged in negative 4 and then squared it, and then minus negative 4 and then minus 20, you'd get a 0. If you plugged in 5 and then squared it, and then minus 5 minus 20, you'd also get a 0. So both of those two numbers work and are solutions to this equation. Let's do another. Let's solve this equation via factoring. Here we have a variable w. We have 2 times w squared is equal to negative 8 times w plus 42. Let's go ahead and solve this via factoring. Before we get started, the first thing I want to do is set one side equal to 0. So what I would end up doing is I would add 8w to both sides. And then I would subtract 42 from both sides. That would give me 2w squared plus 8w minus 42 is equal to 0. There are some fancier factoring techniques that you can do right now on this equation as it sits. I'm not going to go over those. I'm going to say, notice what happens. Each coefficient of the 2, the 8, and the negative 42, all of those numbers are divisible by 2. So I can simply divide both sides of this equation by 2, and that gives me w squared plus 4w minus 21 is equal to 0. Now I have what I want. I have a 1 in front of my squared term. In this case, it's w squared. I'm going to look at factors of negative 21, and specifically, I'm going to look for factors of negative 21 that add to 4. Well, it doesn't take you very long to figure out that the factors of negative 21, the two numbers that multiply times negative times themselves to get negative 21. Let me rephrase that. The two numbers that multiply times each other to get to negative 21 and which also add to 4 are the number negative 3 and positive 7. So negative 3, let me just write, times positive 7 gives you negative 21, and negative 3 plus 7 give you 4. So I'm going to use negative 3 and positive 7. And I rewrite that equation as w minus 3 in parentheses times, in parentheses, w plus 7 is equal to 0. That's how my quadratic factors. And now we can set each piece equal to 0. So w minus 3 could have been 0, or w plus 7 could have been 0. Solving each gives us that w could have been equal to a positive 3. That's what I get when I add 3 to both sides of the first equation. Or w is equal to a negative 7. That's what I get when I subtract 7 from both sides of this equation. Like I said, I'm doing the most basic version of factoring here. There are other more complicated versions of factoring that you can take advantage of. But typically, if we have this nice version where we have a 1 in front, then that's most of what we need. And if when I divided by 2, I got fractions here, then I'd probably just use one of my other methods for solving the quadratic equation. And that's what we're going to do. We're going to use other methods to solve the quadratic equation if we cannot factor, or at least if we can't factor easily and quickly. Here's another method we can utilize. Now, this one is going to be a very different form. We're going to use the square root method. So we can solve quadratic equations through the square root method. The square root method basically takes this on. It says, what if we have, instead of ax squared plus bx plus c on one side, what if we have x minus h squared on one side is equal to some other value? We'll call that r. So if I can force my equation to look like this, then I can simply say, then x minus h has to be either the positive square root of r or the negative square root of r. And then I can solve each equation. Let's do an example. Let's solve this example, which is example 6, using the square root property. We have the quantity t plus 3 being squared, and then minus 36 is equal to 0. So quantity t plus 3 squared minus 36 is equal to 0. Let's solve this utilizing the square root property. So the first thing I notice is that we have my variable inside of something being squared, and then everything on the outside of that has no variable involved. So this is the situation in which I can use the square root property effectively. The first thing I would do in this case is I'd leave the t plus 3 inside the squared alone, and I'd add 36 to both sides. That would give t plus 3 squared is equal to 36. Now here's what we do. We say, therefore, using the square root property, t plus 3 can either be plus or minus the square root of 36, which is 6. This is actually two separate equations. It's the equation t plus 3 is equal to positive 6, square root of 36 is 6, or t plus 3 is equal to the negative of the square root of 36. So t plus 3 is equal to either positive root 36 or negative root 36. In the first equation, when I subtract 3 from both sides, I get t is equal to a positive 3. In the second equation, when I subtract 3 from both sides, I get t is equal to negative 9. This is how we employ the square root property. Now, I want to mention something. The square root property was very effective on a problem like this. On a problem like this, we don't have our something inside parentheses being squared and then everything on the outside being a constant. So the square root property would not have worked nearly as well. I would have had to do a lot of extra work to use a square root property with my previous example. Also, if I would have tried to factor this, then I would have had to multiply out t plus 3 quantity squared and then did all the other combining like terms and stuff like that. And then I could have a chance of factoring. The square root property is a lot quicker on a problem like this. So there are some problems where factoring is the way to go. It's the quickest version. There are other problems where the square root property is going to be the way to go, where that is the quickest version. Let's look at another example here. Let's solve this equation using the square root property. We have 3 times the quantity x minus 7 squared is equal to negative 75. So let's solve this using the square root property. If you'd like to do this on your own, then just push pause on the video. In a couple of seconds, I'll show you how I do this. All right, so the first thing we want to do is get that x minus 7 squared all by itself on one side of the equation. That's going to force me to divide both sides of the equation by 3. When I divide both sides of the equation by 3, I have x minus 7 quantity squared is equal to a negative 25. Now I can take the square root property. If I do the square root property, I know that x minus 7 is going to be equal to either the positive or the negative version of the square root of negative 25. Now, the square root of negative 25 is not a real number, but it is a complex number. So it's the number 5i. This gives me two separate equations. X minus 7 is equal to either the positive version or the negative version of 5i. We went over complex numbers in a previous video. So if you don't know that the square root of negative 25 is 5i, you can check out that previous video. And then all I have to do is create two equations. X minus 7 is equal to 5i, or x minus 7 is equal to negative of 5i. If I add 7 to both sides, I get x has to be equal to 7 plus 5i. Remember, that's a complex number. Or x is equal to 7 minus 5i. Again, one of those two complex numbers. So in this case, when I solved via the square root property, I got two complex numbers. And if you were just looking for solutions over the real numbers, you'd say there's no real number solutions. But over the complex numbers, we have two of them. The third method that I mentioned was solving the quadratic equation using completing the square. I'm not going to do that in this video. It's a fairly complicated process where we take any quadratic equation and we force it to look like this one, and then we solve it using the square root property. So completing the square means forcing your quadratic equation to look like this, and then solving using the square root property. I don't typically solve using completing the squares in this class. You can if you want. I might show you it, but it won't, any one you can do by completing the square, you're going to be able to do by the next method. The next method that we are going to look at is the quadratic formula method. So I'm going to want to solve quadratic equations using the quadratic formula. Now, in order for the quadratic formula to work, we need our quadratic equation in one variable to look like ax squared plus bx plus c is equal to 0. If we have that form, then the solutions will be x equals negative b, or opposite of b, plus or minus the square root of the quantity b squared minus 4ac all over 2a. Usually we say it as opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Opposite of b plus or minus square root b squared minus 4ac all over 2a. I'm sure many people have seen this earlier in their high school math curriculum. Let's go ahead and use it. Let's solve the following equation via the quadratic formula, or solve it with the quadratic formula. We have x squared minus 6x plus 13 is equal to 0. If you want to push pause on the video and try this on your own, go ahead and do so. Otherwise, I will do it in a couple of seconds. All right, let me go ahead and do this. Now, we already have our equation in the right form. We have ax squared minus, or excuse me, plus bx plus c equals 0. So we have our equation as the quadratic piece in sort of like a general form on the left, set equal to 0 on the right. If we have this pattern, then we can use the quadratic formula. So my x values are going to be opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Now in my example, the b is a negative 6. So I replace every b I see with a negative 6 because that is the coefficient, the b is stand-in for the coefficient of the x to the first coefficient. So b is negative 6 in my example. Be careful because opposite of negative 6 is going to be a positive 6 in just a moment. Then I need to know the a and the c. Well, a is the coefficient of x squared. That is a 1. So I replace each a with a 1. The c is my constant term. That's a positive 13. So c is a positive 13. And then I just simplify. There's a lot of simplification that I can do. First off, the opposite of negative 6 is a positive 6. And then we get plus or minus the square root. Now, what's inside the square root is negative 6 squared. Make sure the negative is in the inside of parentheses. That'll give me a positive 36 minus 4 times 1 times 13. When I do that, 4 times 13 is a 52. So I get 36 minus 52, which is a negative 16. And then that's all divided by a 2. Once again, because I have the square root of a negative number, I do not get real answers, but instead I get 2 complex number answers. In this case, I have 6 plus or minus. When I take the square root of negative 16, square root of a negative is I, square root of 16 is 4. So that gives me 4i divided by 2. And then I can divide both the real part and the imaginary part of that complex number by 2. So I get 3, and then either plus or minus 2i. This is 2 different values. One of them is 3 plus 2i, and the other is 3 minus 2i. So these are the 2 values which are solutions to this quadratic equation. I get 2 complex number solutions to that quadratic equation. 3 plus 2i and 3 minus 2i. Notice, by the way, they came in a pair that were complex conjugates of each other. That actually always has to be the case because when you take plus or minus the square root of this, if this thing does give me an I, then I'm going to get the positive version of the imaginary, negative version of the imaginary. And then the B and the A are going to be real numbers so long as our A, B, and C are all real numbers. So if I have A, B, and C as real numbers, then the only place I can get an imaginary is right here, and the plus or minus are going to cause us to have complex conjugates. So there we go. Those are the two solutions to this quadratic equation. Let's use the quadratic formula to solve this next equation. 2x squared is equal to 5x plus 14. If you want, push pause on the video and try it on your own. In a couple of seconds, I'll show you how to do it on the computer screen. The first thing I need to do in order to solve this quadratic equation is get it into the form that I want. I want 0 on one side. So that's going to force me to subtract 5x from both sides and subtract 14 from both sides. If I do that, I get 2x squared minus 5x minus 14 is equal to 0. Now I can employ the quadratic formula. We know what that quadratic formula is. Opposite of b plus or minus the square root of b squared minus 4ac all over 2a. In this case, b is a negative 5, so I replace every b with a negative 5. Make sure you replace it inside of parentheses when you're plugging it in. The a is a 2, so everywhere I see an a, I replace that with a 2. And the c is a negative 14, so I replace that c with a negative 14. And then it's just a matter of simplification. So x here is going to be equal to 5 plus or minus the square root. When I take this square root, I'll get 25 minus 4 times 2 times negative 14. 4 times 2 times 14 gives me 112. And if I add, that's going to be a positive 112 because negative times negative gives me a positive. And then add 25 to that, I'll get 137 inside that square root. And then obviously my denominator is 4. Now 137 is not a perfect square. So when I take the square root of it, that's going to be an irrational number. Square root of 137 is an irrational number. And I don't think that we have any good factorizations that can simplify that. So what I would do here is I would just stop and say, this gives me two solutions. One, which is x is equal to 5 plus the square root of 137 over 4. And the other, which is x equals 5 minus the square root of 137 divided by 4. Both of those numbers are actually real numbers. So they're not like the previous example, which was a complex number, these are both real numbers. They're just kind of ugly real numbers. They're irrational real numbers. In fact, if you do the calculations, you get approximately 4.18 as that value, the one where we are adding square root of 137. And then when I subtract 137, I get approximately negative 1.68. Again, that's rounding to a couple of decimal places. So I have two solutions. They're both real number solutions, but they're both irrational. Let's solve one more quadratic equation using the quadratic formula. Here I have z squared minus 10 is equal to 3z plus 8. So we'll go ahead and solve this one using the quadratic formula as well. If you want to try this on your own, push pause on the video. The first thing to realize here is that it really doesn't matter what the variable is here on the quadratic equation. We have z in this case. We had x in our last two cases. It doesn't matter what the variable is. We are going to do it the same way. So the first thing I do is I get all of the terms on one side and the other side equal to 0. That would require me to subtract 3z from both sides, and then also subtract 8 from both sides. Negative 10 minus 8 would give me negative 18. And therefore, this equation turns into z squared minus 3 times z minus 18 is equal to 0. At this point, I can use the quadratic formula. Opposite of b plus or minus square root of b squared minus 4ac all over 2a. B in this case is a negative 3. A in this case is a positive 1. And C in this case is a negative 18. And now I simplify. In this scenario, I have 3 plus or minus the square root of, I'd get 9 minus 4 times 1 times negative 18. That gives me a positive 81. 4 times 18 gives a 72. And this is going to be a 9 plus 72, which gives me an 81. And then I divide that by 2. Divide the whole thing by 2. In this case, it's really nice because 81 is a perfect square. So when I take the square root of that, that's just 9. And my two answers are going to be 3. Sorry, let's do 3 plus 9 all divided by 2. Or 3 minus 9 all divided by 2. In other words, my two answers are that z is going to be either 6 or z is going to be a negative 3. So those are the two answers using the quadratic formula. Now I want to point something out. The quadratic formula took a lot of different simplification here. A lot of different places it may have gone wrong. In this example, I could have also factored. And you can tell you can factor when you get answers like z equals 6 and z equals -3. So if I had wanted to factor, I could have actually factored factors of -18 that add to -3 are -6 and +3. And you can see that if we set each factor equal to 0, then we get the exact same two answers. Z equals 6 or z equals -3. Now, this shows you that all of the problems we could have done by factoring can also be done by using the quadratic formula. However, the reverse is not true. If you were to try to factor this, you could not factor this polynomial, this quadratic on the left over the integers. So this would not have factored over the integers. And the same thing is true for our previous problem. If I would have tried to factor this one, I would have not been able to factor this one. So the quadratic formula works on basically any quadratic equation we have, as long as we can simplify it and set one side equal to 0, the quadratic formula will work. But sometimes factoring is simpler. And sometimes using the square root property is simpler as well. When we are solving quadratics, what I usually do is I usually look at it and see if I can factor first, factor easily. If I can't factor easily, then I say, is it looking like something that fits that square root property? If it looks like it fits the square root property, then I'll go with the square root property. If I can't factor it easy, then I jump right down to the quadratic formula. So it's either I check for factoring because that's usually the quickest way to do it. If I can't factor, then if it has that square root property look, then I'll use the square root property. If it doesn't have the square root property look, then I'll just jump right to the quadratic formula. And that's kind of what I do when I solve quadratic equations. Remember, this all came about because we were taking quadratic functions and quadratic equations in two variables, and we knew that the graph was going to look like a parabola, and we knew that we could find a y-intercept by just plugging in 0 for x, and we knew that we could find x-intercepts by plugging in 0 for y. And that was going to, when we plugged in 0 for y, that was going to force us to solve quadratic equations. So this was all about, or all in the vein of trying to solve quadratic equations to find x-intercepts. Let's look at an example. Let's find the x and y intercepts of the following function. F of x is equal to x squared minus 6x plus 5. If you want to try this on your own, go ahead and try this on your own. Push pause on the video. I will do it in a couple of seconds. All right, so let's do this. First off, let's find the y-intercept. For that, we plug in x equals 0. So we take f of 0, and that's going to be 0 squared minus 6 times 0 plus 5, which is just 5, obviously. So that means that the y-intercept is the point, whoops, is the point 0, comma 5. Remember, all quadratic functions are going to have exactly one y-intercept. Now the x-intercepts, you could have 1, you could have 0, you could have 2. I guess I should write x-intercept and then in parentheses s. That might be a more correct way to plug that in. And in this case, I would just replace the y value with a 0. So 0 is equal to x squared minus 6 times x plus 5. We have one side equal to 0, so I can factor the other side. If it bothers you that 0 is on the left-hand side, and we've been factoring with the 0 on the right-hand side, then just go ahead and flip which side the 0 is on if you want to do that, if we want to solve the quadratic equation like this. This is obviously not set up for the square root property because I don't have some sort of a quantity being squared. So it's either set up for factoring or the quadratic formula. Usually what I do is I check factors of 5 that may add up to -6 first. And if I can find that, then I'll just use factoring. So in this case, there are factors that work. We have a -5 and a -1. If I take -5 times -1, I get a +5. -5 plus -1 gives me a -6. I can do that because there's a 1 out in front of this x squared term. Now I can solve. X minus 5 could be either equal to 0. Well, either x minus 5 could be 0 or x minus 1 could be 0 to make that statement true. X it could have been 5 or x could have been 1 to make that statement true. Both of these are real numbers. Since both of these are real numbers, what we're getting is two x-intercepts. So the x-intercepts are the 2 points. One of them is 5, 0. And the other one is 1, 0. I misspelled that. Those 2 points are my x-intercepts, 5, 0 and 1, 0. In this case, if I want to graph just to make sure that I got the right thing, I can double check my work by graphing this f of x. So here is the graph of f of x equals x squared minus 6x plus 5. From our work earlier, I could have found the vertex. I could have found the axis of symmetry. But here we see that my two x-intercepts are 1, 0 and 5, 0. My y-intercept is 0, 5. Obviously, I did this on Desmos. You could graph it on the TI-84 calculator as well if you want to graph that way. Let's do another. Let's find the x-intercepts and the y-intercept of the following function. F of x is equal to x squared plus 4x plus 7. Push pause on the video and try it on your own if you'd like. In a couple of seconds, I will do it on the screen. All right, once again, I'll find the y-intercept first. So plugging in 0 into the x value, into the input of the function, is going to give me 0 squared plus 4 times 0 plus 7, which just becomes a 7. I won't even write the work there. That means we have the one y-intercept of 0, 7. So the point 0, 7 is my y-intercept. Now, again, I'm going to plug in 0 for for the y value to find my x-intercepts. This may lead to 2 x-intercepts. This may lead to 1 x-intercept. This may lead to no x-intercepts. We'll find out here shortly. We have 0 equals x squared plus 4x plus 7. Or, again, if you like the 0 on the right-hand side, just write x squared plus 4x plus 7 is equal to 0. So the output value is equal to 0. If you look at factors of 7 over the integers, it's just 1 times 7 or -1 times -7. Neither of those pairs add up to a 4. So we're going to have to utilize the quadratic formula on this one. This is in the setup for the quadratic formula. So x values are going to be opposite of b, plus or minus the square root of b squared minus 4ac all over 2a. B in this case is 4. Move that cursor out of the way. A in this case is a 1. And C in this case is a 7. Now we're ready to simplify. X is equal to the fraction. In the numerator of that fraction, I get -4 plus or minus the square root. 4 squared is going to be 16. 4 times 1 times 7 is 28. So I get 16 minus 28, which is a -12. Divided by a 2. If you wanted to, you can simplify that. I'll go ahead and keep simplifying just for the sake of this problem. If I take the square root of -12, the negative under the square root is going to turn into an I. 12 is like 3 times 4. I can take a square root of 4, that's a 2. A square root of 3 is an irrational number, so I'll just leave it as square root of 3. So I get 2 times I times square root of 3, or some people would write that as 2 times the square root of 3 times I. I'll write it this way. -4 divided by 2 is a -2. then 2 times I times root 3, all divided by a 2, just gives me root 3 times I, or I times the square root of 3. Notice that in this case, I get two imaginary solutions for x value. Two plus I times the square root of 3, or again, some people would write square root of 3 times I. Doesn't matter which way you write that. Just make sure that I is not under the square root. The I is over there to the side, not under the square root. That's why I tend to put it in front, just so it doesn't look like it's under the square root. So that, or x is equal to -2 minus I times the square root of 3. Both are imaginary. If I were to try to graph these, well, on a Cartesian coordinate system, the x-axis and the y-axis just consist of real numbers, not imaginary numbers. So this is the case where there are no x-intercepts. When my two solutions come out as imaginary, that means that the parabola never crosses the x-axis. There's no real number where we cross the x-axis. Now, we could have actually just stopped right up here. As soon as we saw we were getting an imaginary answer, we could have stopped and said, at this point, I know my solutions are imaginary, and therefore I know that there's going to be no x-intercepts. I kind of went through the entire simplification when I didn't really need to. As soon as I see that there's a square root of a negative number, in our case, that was the square root of -12, I knew I was not going to get any x-intercepts. So there you go. This is that case where we don't have x-intercepts. Again, if you wanted to graph this and see what's happening, you could. I won't graph this one since I graphed the previous one. But if you did graph this, you'd see it's a parabola pointing up. You could find the vertex. You could find the axis of symmetry. You could find the minimum point or the minimum value. And then now you can find the y-intercept and see that there are no x-intercepts. Let's do one more example where we just find the x and y-intercepts of a quadratic function. In this case, we're going to have our quadratic function take that standard form where I have quantity x plus 5 squared minus 2 as the output value of my function f of x. Go ahead and push pause on the video and try this example on your own. In a couple of seconds, I'll do the problem on the computer. As the norm, I'll find the y-intercept first. I do that by plugging in an x value of 0. In this case, that's going to give me 0 plus 5 quantity squared minus 2. And when that's all simplified, I'll get 25 minus 2, which is 23. Therefore, the y-intercept that I just found is the point 0, 23. To find the x-intercepts, if they exist, plug in 0 as the y value. And when I do this, I'll say that the output value of x plus 5 quantity squared minus 2 has to be equal to 0. In other words, I'll put 0 on the right-hand side just because we've done that so many times. Now I can solve this. Obviously, in this quadratic equation with variable x, this is set up for us to do the square root property. All I have to do is add 2 to both sides. That gives me x plus 5. Quantity squared is equal to 2. Now I can take and set x plus 5 to be equal to either the positive or the negative of the square root of 2. To undo a square, we take positive or negative the square root of that number. Square root of 2 does not simplify. It's an irrational number. So I end up with x being equal to, when I subtract 5, it's minus 5, either plus or minus the square root of 2. Be careful on that. This is 2 solutions, one of which is negative 5 plus the square root of 2. The other is negative 5 minus the square root of 2. So those are my 2 values. Now, by the way, these are both real numbers, okay? They're irrational numbers, but they're both real. So we do have 2 x-intercepts in this case. We have one whose x value is negative 5 plus square root of 2, and the other which has x value negative 5 minus square root of 2. So the x-intercepts are those 2 points. One having an x value of negative 5 plus the square root of 2, and then comma 0, obviously. And the other, which has x value of negative 5 minus the square root of 2, and then the y value is obviously 0. So those are my 2 x-intercepts. Obviously, if we wanted to round these x values to whatever numbers they are, you can use the rounded versions of those as well. Negative 5 plus square root of 2 is about negative 3.59, and negative 5 minus square root of 2 is about negative 6.41. So we've just found both the x and y intercepts for this function, the x-intercepts and the y-intercept for this function here. Obviously, this started in that standard form, so the technique that was easiest to do when finding the x-intercepts was using the square root property. In our previous case, when we were finding the x-intercepts, the technique that we kind of had to use was the quadratic formula because this did not factor easily. And in the case before that, the technique we chose to use to find the x-intercepts was factoring, because that one actually did factor fairly easy. One word of caution that I want to mention before we move on to the next is that here my function was obviously in the standard form, and we came out with 2 x-intercepts where our x value was 2 real numbers. But as we could see earlier, by just changing this -2 to like a +8, we could have ended up getting complex numbers here too. So the form that your function looks, if it's in the standard form or if it's in the general form, either way could lead to no x-intercepts or 2x-intercepts or 1x-intercept, depending on the actual form of the function. So again, the x-intercepts are determined by solving this. And we saw earlier that when we solve an equation like this, we could get complex solutions. We could get real solutions like we did here. And the same is true with the standard or the general form, standard form here. We could have a function which is in either standard or general form, or looking like this. Let's say general like this. And that could lead to 2x-intercepts or 1x-intercept or 0x-intercepts. This one led to 0x-intercepts, but using different numbers, we could have ended up with 2x-intercepts. Let's do this last example, example 14. Now, this is actually the example that we had in example 3, where I originally asked, how would we find the x and y intercepts? Now let's find all of the features of this quadratic equation that we mentioned earlier. So we're going to find the vertex, the axis of symmetry, the minimum or maximum y value, the x-intercepts, and the y-intercept, that'll be singular, of this quadratic equation. If you want to try this on your own, push pause on the video. All right, first off, let's search for the vertex. The vertex is going to have x value of opposite of b over 2a. By the way, that looks familiar. That's the first part of the quadratic formula without the square root in it, basically. I'll talk about why that is in just a moment. But what we get is opposite of -2 over 2 times 1. So that gives me essentially 2 over 2, which is 1. So the x value of the vertex is 1. The y value of the vertex is going to be what we get when we plug in 1 into the equation. We get 1 squared minus 2 times 1 minus 5. That's 1 minus 2 minus 5, which is a -6. Therefore, the vertex is the point 1, -6. Now that I know the vertex, the axis of symmetry is just the vertical line x equals 1. This parabola has a coefficient on x squared, which is a +1. So the parabola is pointing up. Whenever a parabola points up, think of it as doing this. So it's pointing up. And that means the vertex is going to be the minimum point. And therefore, the minimum y value is the y value of the vertex. Min y value is -6. Now let's find the x and y intercept. The first thing I'll do is find the y-intercept. To find the y-intercept, I plug in 0 for x. That's y equals 0 squared minus 2 times 0 minus 5. And so we get out a -5 as the y value. So the y-intercept is the point 0, comma, -5. Now we're ready to search for the x-intercepts if they exist. We plug in the y value of 0, which gives us, I'll say 0 is equal to x squared minus 2 times x minus 5. Again, if you like to see that, so 0 is my y value here. If I like to see the 0 on the right-hand side, just put it on the right-hand side instead of the left-hand side. The first thing I'm going to do, since my equation is in this general form, is look for if I can factor. The only factors of -5 are -1 times +5 or +1 times -5. Neither of those add up to give me a -2. Therefore, I need to use the quadratic formula. Opposite of b plus or minus the square root of b squared minus 4ac all over 2a. In this case, the b value is -2. The a value is 1. And the value for c is a -5. And now we simplify. X is equal to a fraction. In the numerator, I'm going to have 2 plus or minus the square root of, when I simplify the inside, that first part is a 4, the second part is a +20, so I get the square root of 24. And that's all going to be divided by a 2. Now we can simplify this even more if we'd like, because the square root of 24, 24 is like 4 times 6. Square root of 4 is a 2. Square root of 6 is irrational and doesn't have any perfect squares in it. So this is like 2 times the square root of 6. This gives me 2x values. One x value is 1 plus the square root of 6. The other x value is 1 minus the square root of 6. Those are the two values. By the way, if I take 1 plus the square root of 6, I get about 3.45. If I take 1 minus the square root of 6, I get about negative 1.45. My x-intercepts, well, the exact values in my x-intercepts are going to be 1 plus the square root of 6, comma 0, and 1 minus the square root of 6, comma 0. Those are my two x-intercepts. And the approximate values would be about 3.45, comma 0, and negative 1.45, comma 0. So now we've found all of the features of the quadratic equation y equals x squared minus 2x minus 5, at least all of the features that we were asking for. Again, we can, if we want to, graph this and kind of confirm that I get about the right answer. I say about the right answer because when you look at the x-intercepts through graphing, these will not come out as exact values for x, but rather they will come out as the decimal approximations on either your graphing calculator or on Desmos. That graph on Desmos is right here. And again, I'll do this on Desmos, but you could also do it on the calculator if you like. Sure enough, 1, negative 6 is our vertex. That minimum y value on all of our graph is the negative 6. We cross the y-axis at the y-intercept of 0, comma negative 5. You see the two x-intercepts, again, about 3.45, comma 0, and about negative 1.45, comma 0. And then the axis of symmetry is obviously x equals 1. We said that as well. Now, this is the thing I want to mention. Remember that the vertex is negative b over 2a, and that's kind of the first part of my quadratic equation. Well, that's not by accident. The negative b over 2a gives me the middle line. X equals negative b over 2a gives me this middle line. And you can see that whenever you cross the x-axis, because this axis of symmetry is symmetric, you have to move left and right by the same amount. That's kind of like that plus or minus the square root of b squared minus 4ac over 2a. That part is the movement left or right from how far from your x value of your vertex. So because of the symmetry, that's why we get negative b over 2a. That's one reason we can think of it. The other reason is through a process of like completing the square, you can come up with the quadratic formula. I won't go through that part right now, but there'll be a companion video on completing the square if you're interested, and how that relates to both the vertex and the quadratic formula. So symmetry from the x value of our vertex tells me that the vertex has to be at opposite of b over 2a. That's one of the ways I can think of it. Again, algebraically, this plus or minus part is moving you from the x value of your vertex. If I don't move at all, I just get opposite of b over 2a. That's the x value of my vertex. So that's example 14. And that basically is this entire features of the quadratic equation in a nutshell. All of the things we looked at in this video, the vertex, the axis of symmetry, the minimum or maximum y value, the x-intercepts, the y-intercept, and then we saw the graph of that quadratic equation. So we can do all of those things with quadratic equations and quadratic functions.